In the previous video, we introduced the graphical data structure. But in today's video, we are going to study the greedy algorithms under graphical data structures. Now let's look at the greedy algorithms. A greedy algorithm is used to provide optimized solution to a given problem. You might begin to ask, what exactly is an optimized solution? Now, let's use this scenario to explain what an optimized solution is. Assuming I am required to travel from Southampton to Heathrow Airport, you will agree with me, and I am given the opportunity to choose whichever transportation system I want to use. In that case, I can decide to use a bicycle, a cab, a train, or use the flight to travel from Southampton to Heathrow Airport. All these means are possible solutions to the problem of traveling from Southampton to Heathrow Airport. However, if the condition is that I must be at Heathrow within an hour, then using a bicycle or a cab or the train means of transportation might not guarantee that I will reach the airport within an hour. But if I decide to use the airline system, then I'll be guaranteed to get to the airport within an hour. So in this problem, we have different solutions to the problem. And those different solutions are possible solutions. However, the only optimized solution to that problem is the airline system, because it guarantees that I will be at the airport, all things being equal, within an hour. So this is how the optimization works in greedy algorithms. But one thing is important to note, that that thing is that the greedy algorithm provides optimized solution. However, the optimized solution might not be the global solution to the given problem. For instance, if we use the same scenario, we will realize that even though the airline system guarantees that I will be in the airport within an hour, however, the cost of going to the airport using the airline is possibly going to be higher when compared with other means I would have used to get to the airport. So in this case, the greedy algorithm provided the optimized solution, but has failed to provide a global solution to the given problem. Now, if we go through this slide, the first bullet and the second bullet state that in greedy algorithms, a decision is made at each state that appears to be good, but no consideration is given to future consequences of this decision. And the second bullet says that once decision is made, it is never reconsidered. These are the problem. The greedy algorithm provides optimal solution, but sometimes doesn't provide the global optimal solution because a decision is made and that decision can never be reconsidered. So even if the decision that was made was not the correct decision or the best decision to make at that stage, you cannot go back to correct such decision again. There's no opportunity to go back and correct the decision or take another decision, alternative decision from what you have taken before. Now, we are going to give an example to further explain what the greedy algorithm is and how it can sometimes give or wouldn't give the global optimal solution. Now, the example is looking at a problem of changing coins. So we are required to change a given amount of money using the minimum number of coins. And the currency we are using is the UK currency. So in order to achieve this, in order to ensure that we use the minimum number of coins, and we are going to use the largest denominations first before using the smaller denominations. So in this case, we are considering giving a change for 65 pence. So the largest denomination coin that we will get is 50 pence, followed by 10 pence and 5 pence. So this is an optimized solution to the given problem. However, if we introduce 12 pence coin, then the greedy algorithm will take the largest denominations, which are 50 pence, followed with 12 pence, followed with 2 pence and 1 pence. And if you look at this second scenario, you realize that the greedy algorithm only considered the largest denomination constraint, but failed to sustain the minimum number of coins that are required. So in this case, we have tried to explain the problem of greedy algorithm as it relates to the global, to finding the global solution to a given problem. Now, we are going to move into the applications of these greedy algorithms. One of the applications we'll be studying today is the shortest path trees. The shortest path tree are used to find the shortest distance or shortest path leading from one point, which are going to be called vectors in this lecture, to another vectors. In a real life scenario, the shortest path tree can be applied to find the shortest path or the fastest route from one home to a given place. And that can be found in the road map that we use to find the distance or the fastest route to lead us from one place to another place. Another example of these applications in the real life scenario is the airline system. In the airline system. So in the airline system, this approach can be used to find the quickest or the cheapest route from one airport to another airport. In this lecture, we have used source vertex and sink vertex to represent the starting point and the ending point of the transportation or the link between two vertices. Now let's use this to explain the shortest path scenario. The question here is for us to find the shortest weighted path from A to F. So we have a graph given, and we want to find the shortest path that will lead from A to F. To solve this problem, we'll first look at the possible paths that can lead from A to F. So the first possible path is the path that leads from A to B, B to E, E to G, and G to F. But is this weight the lowest or the shortest weight that we can find? How do we find the weight? The weight will be addition of all the weights attached to the edges that form the path. If we get the weight, we end up having 19 as the weight to travel from this A to B to E to G and to F. If we check other means to travel from A to F, we also have different numbers that has different weight. But the only one that guarantees the shortest weight is the path that goes from A to D, D to G, and G to F. So this is the only path that guarantees the shortest or the quickest path from A to F. And this quickest or shortest path also has the lowest cost. Now, we are going to look at the Dijkstra's algorithm. So Dijkstra's algorithm makes use of the singly source shortest path algorithm or principle. So what it does is that it finds the shortest path from a given vertex to all the vertices within a given graph. So in the previous one, we were concerned in finding the shortest path that leads from A to F. But the Dijkstra's algorithm is concerned in finding the shortest path that leads, for instance, from A to all other vertices within that graph. Let's use this as an example to illustrate what and how the Dijkstra's algorithm goes about finding the shortest path between a given vertex to other vertices within a graph. Now, we have been given this graph, and we want to find the shortest path from A to every other vertices within this graph. So to achieve that, we first of all start from A and look directly from A to find out the vertices that are directly connected to A.